Today's presentation will be given by Krishna Panthi on effect on waterway tunnels due to frequent operational changes in hydropower plants. So thank you very much for presenting today, Krishna, and I'll just hand over to you.
Thank you very much, Berit. So it is my pleasure to talk in this launch webinar. So today I am discussing about the effect on waterways or pressure tunnels and shafts due to frequent operational changes in hydropower plants. So this we have done some research during HydroCen period, and these some findings will be presented here, and then I will at the end discuss about what we are going to do during this RenewHydro period. So there have been mainly 3 research issues that were investigated during HydroCen research period. And the first one was the assessment on the swelling and disintegration potential of weak and weathered rocks. So this issue was more relevant for, especially for international hydropower development. But also in Norway, we have weakness zones that holds quite a lot of swelling clay. So this is also needs to be investigated, of course. And second one was optimization of test methods and design of transition zones in online pressure tunnels. And the third one was a long-term impact on online pressure tunnels and shafts of hydropower plants due to frequent start-stop. So this is the issue that I'm going to discuss today. So other 2 issues can be discussed sometime later, maybe in future. And so background on why operational changes happened in Norway, I will first discuss about it. So until 1991, we have had almost constant operational scenarios in Norwegian hydropower plants because there were annual agreement with local communities and industry. So how much energy they need all the time. And that was a fixed operational system. So then there were not that much start-stop sequences in a year period. So there have been very few. And in 1991, Norway has decided to deregulate its power market, and that led to the changes in operational scenario. And in the meantime, after 2000, especially intermittent energy sources like solar and wind have been expanded. And also Norwegian national grid connection to the Europe and UK has been made now. So, and that makes a change in operational regime. So if we look on this pie diagram, we can see that the different types of this energy systems that are applicable in European market. So the hydropower covers almost 11%. If we look, this scenario will be predicted for 2050 by Statkraft. So it means there will be a huge change in energy market in Europe. So it means the main battery system to balance this market is most likely hydropower, because it has potential to store the water in the reservoir as a battery, and then it can be used when the price demand is high. So in that context, being Norway almost 60%, a country that has almost 60% reservoir capacity of Europe, so then it has quite a lot of impacts on it. So as a result, so we can see here we have collected from some 10 different hydropower plants how the operational regime is right now. So you can see here every year we have start-stop or operational change scenario of up to almost 850 maximum, and then minimum up to 100 times. So this is very dramatic, and then this will increase more and more. So this changes will have not only impact along the waterway system itself and to the turbine and generator, but also it will have impact to the tunnel's outside tunnel wall on the rock mass. So how it happens, I will show you. And then if we look on an operational situation of start-stop. So for example, we have off situation and we have on situation and we have again off situation, and we may have also load changes. So we start the plant, come to the maximum operational point, and then we reduce slightly and again reduce slightly and then do the stop. So this is the typical scenario nowadays in Norwegian hydropower plant. So that operational changes varies from 20 to over 100 times a year, with typical mean of about 350 times per year based on these 10 hydropower plants study. But there are many other plants that are even more dramatically operated. So this has changed variation in pore water pressure in the rock mass, because in the rock mass, Norwegian waterway systems are online. It means the water has a direct contact with the rock wall. In the rock wall or in the rock mass, there are different joint systems. So from where water penetrates to the rock mass, so that will change the pressure balance between the water in the tunnel and in the rock mass. So to study that, we have made instrumentation. So for example, I'll show the damage that may take due to these changes. You can see the 4 different pictures. So here you see this is a very solid rock mass, almost no joints, but because of this operational change, so there was one joint here naturally, and other were created due to the operational change and the pressure variation between tunnel and rock mass. And here you see to the upper block, huge blocks are falling down from a tunnel that was inspected. Here you can see a very huge wedge failure from the left wall side of this tunnel. You can see, and the rock block is on the tunnel. And here, completely collapsed tunnel in the circuit line tunnel. So these are the main scenarios that are being happening in tunnels. And of course, many of these tunnels are not stopped. Still, they can be operated, but there will be some more hydraulic loss, and then over the time, the accumulation will increase more and more. So this needs to be somehow balanced. What to do and how to operate our hydropower plants is very important to make a strategy to. So why it happens is that, so we have a design principle of the tunnel systems or underground plants for hydropower that governs by 3 main criteria. That is the vertical height from the exposed rock to the position of the tunnel, somewhere here, should be always more than water pressure divided by the density of rock multiplied by this cos alpha, which is the inclination of this tunnel or shaft. And another criteria is the shortest distance from the topography to the tunnel should be more than water pressure divided by the inclination of this valley, cos angle of inclination of this valley, and the density of rock. And third criteria is the minor principal stress in the rock mass must be always more than water pressure. So most of our hydropower plants, they fulfill these criteria. But these criteria is to ascertain that the water is not leaking out of the tunnel, but when it comes to the failure inside the tunnel, so then this is a different story. So therefore, why these things are happening are very important to study, of course. And that was the main interest for the hydropower industry, and then they asked us to do this research. And if we look this design concept of these using 3 criteria, So then there had been the use of the safety factor of 1.3. So during normal period, and if there is a upsurge condition, so it may go down to 1.1. But as you see, this is a tunnel and which is pressurized with water. And then there are joints in different direction in the rock mass, and then water flows through these joints. And then this normal stress perpendicular to this joint must be more than the water pressure. So that will of course hinder not to have leakage far away, but near the tunnel still water pressure is fluctuating here, and then water penetrates here, and then these joints will have a change due to operational variation. For example, if we have a sudden stop of the tunnel, so then there will be a water hammer along the tunnel wall, and then that will also affect to the rock mass and penetrates into the rock mass. And when there is the water hammer is slightly closing down, still there will be a high pressure in the joint. That will make a difference between the pressure scenario. So to study that, so we made an instrumentation at RenewHydro project. So just downstream of this source shaft and then upstream of Fenstock here in this location. So we have had access tunnel from here. This is the concrete plug here, and this is access tunnel and reaching to the header system here. From here down towards the powerhouse, this is a steel pipe up to here. So we did pore pressure variation measurement in these 5 different holes and in the tunnel itself, how it impacts to the tunnel and how the rock mass and the tunnel are interacting each other. So to do that, so then we made instrumentation here. You see there are some pipes that are coming from both walls, coming out to the tunnel. And then there are these plugs. Through the plug, the pipes are taken down, and then there are sensors that are kept here, and then pressure is monitored here in this box, which is a data logger. So it logs at least one data in 10 seconds. There are millions of data available for this from this RenewHydro project. So studying this data, so we have found very interesting results. So before I go for that, so let's look on this situation. For example, here the constant water flowing in the power plant, and there is a steady flow, and suddenly when we make a stop, so then there will be a water hammer, and then the water hammer calms down and it converts to the long-term oscillation, right? So this dramatic increase in pressure and then long-term oscillation will have a huge impact to the rock mass. So it means the oscillation goes from source tank up over, and water hammer is effective in this area if the source tank functions very well. So, but that water hammer is also converted to mass oscillation after this is seized. So the monitoring that we have made indicates that we have, you see here, this is a tunnel water pressure, which is red line here, and then borehole 1, this is this blue line, and borehole 4, this is a dotted line here. And then there are not, they don't follow actually exactly the parallel pattern. So there is some places the water pressure in the borehole is low, and some places water pressure in the borehole is more than that. So if we look more nearer to these, so for example here we have this water pressure in the tunnel. This is a blue line, and we have this dotted line with the pressure in rock mass. So here pressure in the rock mass is slightly below than the pressure in the tunnel, because water has to penetrate first through the joints, and once it reaches to the peak, so then it goes down sinusoidal. But if we look on the rock mass, so then here we have more water pressure in the rock mass than in the tunnel. It means the block is pressed down towards the tunnel. So when we have a high pressure in the tunnel, so then water will press rock blocks towards the rock mass, and when there is a less water pressure in the tunnel, and the water pressure in the rock mass will press the block towards the tunnel wall. So this scenario we call the difference here is a time lag. This is what the terminology we have used. And then if we look detail here, so you see here, this is the time lag. So then there is a accumulation of additional stress here. That stress, even though it is in very small scale, not in megapascal, it's in kilopascal, that millions of time or billions of time of these changes will have impact to the rock mass. So it means, and then also this water hammer is even more dramatic because it will also influence to the pressure, huge pressure change in the rock mass. So that will create a kind of hydraulic stress. So this hydraulic stress which we give the terminology as hydraulic impact, will have a impact to our tunnel system, tunnel and pressure tunnel and shaft systems. So if we look here, for example, if we look on the effect of shutdown, so if we shut down the power plant very robustly within say 50 seconds, so then the transient and tunnel, for example, if we look on this transient one, if we take little more time, so then this is the transient in tunnel, for example, this red line, and then the transient 2 and transient in the joint. So this is a blue line. So it means they almost go parallel if we slow down the stoppage. But if we do it in very rapid way, so then the difference will be huge. So if we look here to the figure here, right? You see here, this is a shutdown of about within 60 to 75 seconds. So then most of the hydraulic impact will be quite high, more than 2 megapascal second. But if we wait and take little more longer time, so then say from 125 to 175 seconds, which means about 2 to say 4 seconds, 4 minutes. So then the same hydraulic impact will be much less. Meaning that if we operate our hydropower plant in a better way, taking little more time, so then the impact to the rock mass will be much less. This is what we have a finding. So it means slower shutdown will give the rock mass time to respond, which helps to reduce time lag between pressure peaks, thus reducing the hydraulic impact. So then this is one way to save our online pressure tunnel, of course. And if we look on the long-term perspective, so then this why it happens. This, even though this is a small forces, so still we have these rock blocks falling, because say we have a tunnel here and we have one joint going this direction and another joint cross-cutting here. So then if we look on different points A, B, C, D here, so then the water will first penetrate to air. So let's see here in the legend here. So tunnel pressure, which is this green line, going up and down during this operational changes. And then if we look on different points, so the situation or hydraulic impact will be different, right? Accordingly, the load scenario will change. For example, when we are at the beginning phase of start or stop of the tunnel, So then the pressure distribution will be like this in all points, almost similar. And so once we have in time t1, so then the pressure will be increased in D and then slightly less to B. And if we reach to time 2, so then it will be negative pressure in one area and positive pressure in other area. And then if we go to time 3, so then even more negative pressure here. So on that way, there will be an unbalance in the pressure development. So that will lead the pressure transients will lead to the long-term fatigue, because same rock block will experience in different scenarios over the time. So that makes a kind of new development of new cracks somewhere here, which is the fatigue crack. So that needs to be investigated even more detail. So we have that plan during RenewHydro. And so what are the contribution factors to this is that one is joint orientation and potential rock blocks. For example, here you see here we have one joint, and then this is the fatigue damage, and this is also fatigue damage. So due to fatigue, this block has fallen down. And here you see here, this is a huge rock block that detached from the rock mass. So that because we have one joint sets from here and other joint sets from here, and then there is some fatigue here, long development of new joints, and as a result there is a collapse here also. So this is one way. So another contributing factor is deformational response of the rock mass. For example, hard rocks like granite, quartzite, and granitic gneiss, many other these hard rocks, they are much stiffer, and joints will the joints need much higher fatigue limits. They have a higher fatigue limits, meaning it takes little more time for the block fall to occur. However, if we have rocks that are more deformable in nature, so then the deformable nature or weak rock mass, so then the stiffness of these rocks are less, meaning E modulus is much less. So then they are unable to tolerate a larger number of pressure transients. So we have most of the Caledonian mountain series where we have most of the hydropower tunnels. They are located into more schistose rock mass. So mostly these type of damage we see along these areas, along the Caledonian mountains. So in comparison to other tunnels to the west or eastern part, so along this Caledonian mountain from all the way from Grimstad all the way to the northern Norway, so we have quite schistose rock mass. So then they will lead to the deformation like this, because the rocks are schistose and then they have less stiffness. So it means the main finding of this research is that we have found that 200 to 400 start stops and more than 1,000 load changes of varying magnitude occur every year per generating unit of the hydropower plant. So there will be a further increase in this trend due to increasing share of underground unregulated power from wind, solar, and other sources from Europe and from within country. So the start-stop sequence cause pressure transients in the tunnel, which have significant influence on the pore pressure variation in the rock mass due to time lag between pressure in the tunnels and pore pressure in the rock mass. This change needs to be taken care. So the pressure transients found to be the source of hydraulic stasis in the rock joints, which cause rock mass failure in online pressure tunnels and shafts. So the shutdown start duration directly affects the time lag. Shorter shutdown starts duration, faster speed causes significant hydraulic stress in the rock mass. So if we take little easier to shut down, so then the same tunnel will be much longer, safe, meaning the lifetime of the tunnels will be increased substantially. So this is what is important issue that the hydropower operator should take care. So with this, the issue during this research period, we have two issues. There are many issues, of course. The grant given us are on these two issues. So one is research program 1.1, new hydropower plants design and construction. So here we have a title, development and documentation of new design methods for evaluation of rock stress for hydropower tunnels and underground powerhouses. So this PhD research will start from August. So then there have been position opened, and then we are in the process of recruiting the new fellow. And another research item is within 2.2, sustainable upgrading and expansion of the hydropower systems. So the tentative research title is Study on Rock Mass Fatigue and its impact on the lifetime of first tunnels of hydropower plants. So this is a continuation of the presentation that I have given right now, and this is the presentation. This is the issue that needs to be looked on this design criteria itself that I presented earlier. Because even though we fulfill all these three criteria, there have been some failure cases in hydropower plants. So there have been hydraulic fracturing or hydraulic jacking, and water leaked out of the tunnel. So these needs to be protected. So then we will make some changes, design changes, principles. So that will be both for waterway systems and underground powerhouse cavern. So these are the two issues we will be discussing. So this presentation is based on our work that we did during HydroCen period. And then we have had this PhD fellow, Vivek Neupani, who was very active in doing this research. And then myself and Kaspar Verede, we were two who supervised him. So there are many publications associated to it. So then these are available online, of course, within HydroCen or NVQS web page, and within NTNU system, library system, and most of these publications are open access. So then you can also download directly from the journals. And also you can find these within our ResearchGate portal, of course. This is what I wanted to discuss with you. Thank you very much.